from Dartmouth and then got her PhD at the Virginia Institute of Marine Sciences. That's in Virginia. And then is now an oceanographer. She went from there immediately to an oceanographer position at the Army Corps of Engineers, and she works at a special place called the Field Research Facility, which is in Duck, North Carolina. It's just, you'll see some cool pictures, I'm sure. So it's a special place because it has infrastructure to measure detailed coastal processes, waves and sand moving around, that sort of thing. So just a stunning, I'm jealous is what I'm saying. So we've been working with her, analyzing data, trying to treat models and data in similar ways for these coastal process problems, collecting new data sets. And so we've been doing this for quite a few years now, and so it's about time she's come to visit. Florida did not suck while she was here, so arranging the weather. So I'm going to just turn it over to Kate.
All right, sounds good. Well, thank you everybody for coming. It's exciting to be here. Oh, there we go. All right, so like Nathaniel said, I work for the Corps of Engineers at their field research facility. It's part of ERDC, which is sort of the R&D research side of the Corps of Engineers. So we're not the ones that are really, building bridges or doing beach nourishments. It's more on the R&D understanding side, trying to figure out what's going on. This is a picture of the field research facility where I work in Duck. We've got a pier that goes out. It's about 25 feet of water on the end. It's the longest pier in the U.S., or so I've been told. And we own this sort of whole block of property. You can see it has the only part that hasn't been developed. And there's a cross-shore array of wave gauges that extend all the way out to the continental shelf in line with one of NOAA's buoys, and so those are measuring wave transformation coming in towards the coast sort of continuously in real time. So you can pull up our website at any time and find out what the wave heights are moving in a cross-shore transect towards the coastline. So just a little bit of background of what the FRF is, because I didn't know how many people were familiar with it. Our mission statement is to advance coastal science and engineering through observational research, and we do that utilizing long-term collection of data sets, sort of assessment of new technologies for collecting data, as well as the performance of numerical models, and also some of the development of unique observational equipment and collection tools. And one of the things that the FRF specializes in is the surf zone. The surf zone is notoriously a really difficult place to work. There's big waves, especially during storms. It moves a lot of sand around, so it's difficult to put an instrument on the bottom and make sure you can get it back and get good data out of it. And the guys at the field research facility have been doing this for almost 30 years now, and they're the best of the best in the business, and it's really exciting to get to work with them because I can come to them with a crazy idea of an instrument I want to put somewhere, and they can figure out how to make it happen. So it's a fun place to work. I think we are missing a slide somewhere. Okay. Not sure what happened. Okay, so the slide we're missing was a little bit of the motivation about what my research is. And so I really focus on trying to understand what happens to the beach during storms. And so one of the problems with doing that in the past has been oftentimes our pre-storm data set is really out of date. And so if we're trying to figure out or quantify and understand what the impact of the storm to the beach is, we haven't really had good pre-storm conditions to compare that to. And then on the flip side, most of the ways that we've studied storm impact to the beach is we go out before the storm and we collect a lot of data, and then we go out after the storm and we collect a lot of data, and we do a comparison between those two data sets, which is great for saying, okay, what happened over the course of the storm, but we don't really have any data that was collected in the middle of the storm. So if you want to figure out why your model prediction at the end of the storm wasn't that great, you don't really have anywhere in the middle of the storm to go back through and to say, okay, where did we start diverging and why? And so a lot of my research is focused on coming up with ways to actually collect data during the storm, and then hopefully to collect it over a wide enough spatial area that we can start to improve our understanding of some of the alongshore variability of that storm impact. So one of the ways that we are able to collect data during storms is using remote sensing technologies. If you can think about it, the surf zone is a pretty gnarly place to be in the middle of a big storm event. You don't want to be in a boat collecting data, but you still want to know something about where the sand is moving around and what the waves are doing over a spatial area. And so with that, we turn to remote sensing capabilities. That's using things like video cameras or radar or even LiDAR technology to try to observe the beach from a remote or removed location. And sort of the grandfather of coastal remote sensing would be the system we call Argus. It was developed out of Oregon State University, and they were sort of the first ones who started looking at the surf zone using video imagery. And so a lot of the analysis and the techniques that we use today was out of the Argus development. And so I wanted to start with that and sort of introduce a couple of concepts that I'm going to be talking about and showing you more data using different technologies, but it can all be related back to the video imaging. So we've got this tower on the FRF property, and at the top of the tower there are a bunch of video cameras that are continuously observing the surf zone. And what's great about that is we get continuous observations for a very little amount of money. It's costing a person's time to go out and collect data. The video cameras are just all automated themselves. And so these are the different views that you see along the coastline. That you can see the pier in this one. And what I'm showing you here is not what you would think of as an instantaneous frame or snapshot of the beach. What this is sort of a time lapse or a time average. So if you stare at the coastline for a period of 20 minutes, say, what did the beach look like on average over those 20 minutes in that one spot? And what you see is, oops, oh no, oh no. I don't know what this is doing. Okay. All right. So what you start to see are these patterns of wave breaking in the surf zone. So this is the beach here. This is the pier where you see white. When waves break, they look white. That's a really easily viewable signal in the remote sensing data. And if you say, on average, where were the waves breaking most often over the 20 minutes that you looked at the beach, you can actually start to map out what the morphology of the sandbars look like. And so what this white streak you're seeing here is what that sort of surf zone sandbar looks like as observed from the video camera. And this is sort of a basic product that we can get out of remote sensing, which has a lot of uses. And then this video, which I think I have to click to play, and I don't know how to do it other than this. So this video here is a time lapse of these images from one of the cameras spanning about 10 years worth of data at the FRF. And some take-home things from this video that I really want you to look at is, one, how a longshore variable the sandbar is. It's not just a continuous straight line along the coast. It's wiggly sometimes. It moves offshore. It moves onshore. And so it's not the same everywhere. And then the second thing is it changes a lot. The beach in the surf zone is really dynamic. It changes hourly, it changes daily, it changes seasonally. And so if you can think about trying to assess or predict what the impact to the beach is going to be from a storm with a year-old survey of what that beach looked like, you might get a really different answer than what the beach actually, using what the beach actually looked like right when the storm hit. And so a lot of my research is sort of about how can we measure this better, and then what are the impacts of the dynamic variability of this region on our predictions for storm impact. So, Argus is great, but it's only at the FRF. It's on a tower. It only looks at a little 1 kilometer stretch of the beach. And a lot of the impacts that we're trying to measure from storms are varying on kilometer scales, or even less than that, along a really large stretch of coastline. So we had to develop a tool that would allow us to cover a really large stretch of beach fairly rapidly and collect the same type of data. So we developed Claris, which is coastal LiDAR and radar imaging system. I think I'm going to get the movies play again. And what we have on it, we have a terrestrial LiDAR scanner, and that's the data that you're seeing in this bottom movie here, and that's used to collect the topography of the beach. So it's just like airborne LiDAR, which some of you may be more familiar with, but it's mounted to the truck. So that's the idea that you can shoot a beam of light out, and then the light reflects back to the scanner, and you know the time it took the light to reflect back and the angle that you shot it out at, and so you can figure out what the topography of the beach is. And it does it at a very high rate, so we get really detailed measurements. You can see the truck tracks, you can see footprints on the sand, so really high spatial resolution data. And then the other part we have is an X-band radar system, and it's just the same type of radar that you might have on your boat if you're going out in the fog or anything like that. And instead of using the radar to reflect off of boats or any obstructions nearby, we use it to reflect off of the incoming waves. And so instead of waves appearing white like they do in the Argus imagery, here waves appear this bright red color. So the radar gives you a really strong reflection off of anywhere you have either a foamy breaking wave face or a steep wave face. And so you can do similar types of things that you do with the Argus video imagery using the radar data. And so this is an example here. This is actually from Fire Island in New York and some work that we worked with Cheryl on. And so this is offshore, this is on the beach. You can see the dune line. This crescentic sort of feature you see in the dark red, that's waves breaking over a crescentic sandbar. And then this in here, this is the inner surf zone, and this is the swash. And so we use this to sort of measure the morphology of the surf zone during the storm event and see how it changes. One of the great things about this is that as long as there is a beach to drive on, we can go out in any condition and collect this data. And so this allows us, this here is the black line is showing you a plot of wave height. So that big peak you see in wave height there, that's a storm event. And these colored lines are showing how we've gone out every day during the storm event and collected data to really track the spatial, both the spatial and the temporal times that we see erosion or accretion during the storm event. Oh, and we're going to play again. There's the motivation slide. I just went through this and it was not out of order, which is weird. But okay, so this is an example of what you can then do with this Claris data. This is now looking at the beach data. And so from that terrestrial LiDAR data, you can create a digital elevation surface or digital elevation model, a DEM. And then you can look at differences, subtracting those DEMs as you step through the storm. And so then this is plotting this is between two surveys looking at the storm impact to the beach. The green colors here are, I believe, the green colors are accretion, and then the red is erosion here. And so you can see there are places where it's really focused, and then there are places where there's less, and so you can see the alongshore variability. And this is just sort of a cool gee-whiz shot of, this was after Hurricane Sandy on the Outer Banks, and this is somebody's pool that is now on the beach that used to be in the dune. And so this just sort of really shows you the level of detail that you can get with the LiDAR scanner. So that's one of the techniques we use to collect data. So now what do we do with that data? And so one of the first things we did was we looked for relationships between what was going on in the surf zone with what we saw on the beach during these storm events. And so in this top plot here, this is one of those radar time averages, and so the bright colors is where you see lots of wave breaking, and then the deeper blue colors is where you see less wave breaking. And so what I've done down here is I've sort of drawn an interpreted version of that colored mess to make it a little bit more understandable. And so what we have, this is along a stretch of beach in Kitty Hawk, North Carolina. What we have here is we have an outer storm bar where the waves are breaking, and then we've got this little inner surf zone bar. So this is the second sandbar that's along the coastline. And what you can see with this second sandbar is that in some places it's well offshore of the beach. You can see waves breaking on the outer bar, on the inner sandbar, and then right at the shoreline. And then in other locations, it's sort of what I've called welded to the shoreline, or a merged swash bar type thing. And so you get different amounts of wave breaking moving across the surf zone because of the morphology of the surf zone sandbars. And if you remember back to that first video I showed you from Argus, the morphology of the surf zone sandbars can change very frequently. And so knowing what that sort of morphology is before the storm event could be really important. And in fact, what we found in this bottom plot, what I've plotted here is the blue line is basically, you can think of it as a proxy for how much breaking occurred in the surf zone. And so what I did was I sort of integrated the radar intensities, which are a proxy for how much breaking there is. So where that number is higher, where you have more wave dissipation. You're breaking more of the wave energy in the surf zone. And where that number is lower, you're breaking less of that wave energy. And so what we found was if you integrated that, it correlated very strongly with the volume change on the upper beach during the storm, and that was a significant correlation. And you can even see it's explaining, some of these. It's even getting some of these little wiggles correct, which are sometimes the hardest little wiggles to predict correctly when we're trying to do shoreline change. And so this region here, where we really only had waves breaking over one sandbar. Sort of the hypothesis that came out of this was, hey, maybe there's more wave energy reaching the beach. And so you have the potential for more storm impacts, maybe higher wave run-up, because there's more wave energy reaching the beach. And so, okay, this was one storm. We wanted to see, do we see this in other places? How ubiquitous is this? So this next storm that we have, this is also on the Outer Banks, but this is over a 20-kilometer stretch a little bit farther north in Duck, North Carolina, so sort of near where the facility is located. And this is a nor'easter that happened after Hurricane Sandy. So Hurricane Sandy was in the fall of 2012, and then the March 2013 nor'easter happened after that. And if you look here, we had waves that were sort of 3 meters or higher, which is pretty big for us for an extended period of time. And we were able to go out every day during this storm and with Claris to survey the beach. And so what did we find? So this top plot here is showing you a section of the region that we surveyed. And here I've overlain sort of those radar wave breaking intensities over the Google Earth image. This is the pier at the facility. And what you can see, there's a pretty continuous wave breaking over this outer storm bar. It's actually fairly alongshore, which doesn't happen a lot. Usually you've got some along irregularities, but in this case, this bar was pretty alongshore uniform. And then this is showing you the wave breaking in the inner surf zone. And then if we look at the storm impact that we saw, so this is doing a surface difference between two of the DEM surveys on either side of the storm. What we saw was there was this region of really concentrated erosion right in here. And if you look here, the colors, the bright pink you're seeing are really high rates of erosion. So pink is erosion, blue is accretion up here. Anywhere that's white, those are changes that are within the error bounds of the two surveys, so you can think of no change. And so you can see up here on this dune line, this really bright pink color. We saw up to almost 6 meters of dune retreat along some of these stretches. So that's a lot of dunes that disappeared during this stretch. And looking at this, at first we thought, well, there's nothing really in the surf zone that's giving us any hint to what's going on here. But when we actually zoomed in a little bit closer, back to this, looking at this inner surf zone, because we didn't see much alongshore variability in this outer surf zone bar, so we looked then to the inner surf zone because that's what we found during the last storm. What we found was that in this region where the erosion was really concentrated again, there really wasn't an inner bar. There was a wide swash zone. So this is now taking a transect across this radar profile, and you've got wave breaking over the outer storm bar out here, and then you've got wave breaking at the shoreline right here. But if you move just out of that region, what we actually found was there was a double barred system again there, and you can see it in these. It's sort of fine scale details, but if you actually take a transect, you do see two peaks, and that's sort of what we use to add quantitative analysis to this, is we calculate the peaks, and that's telling us how many peaks in wave breaking there are as you move towards the shoreline. So we had this double bar feature as we moved out of the highly erosive area. And then if you take the transects on the beach, this is showing you, this is in that erosive area where we have, this is on that same A transect where we have a lot of dune erosion. And then this is just on the edge of where that bar sort of starts to move offshore a little bit, and you've got those two peaks in wave breaking at the shoreline. And so once again, that pattern seemed to hold. And so, okay, so it seemed to be supporting the hypothesis, but we really don't have any data yet on the physical processes. Can we measure, wave height and see if there is really a difference in wave height? And then theoretically, that should have implications for wave run-up, but we need to actually make some of those measurements. And so to do that, we need really detailed measurements of wave run-up during storms. So what that led to was saying, hey, can we take our LiDAR scanner and can we point it at the surf zone? And instead of using it to reflect off of the beach, let's see if it can reflect off of the water surface. And this is a terrestrial LiDAR scanner, and so the wavelength that it is not really suited for use in looking at the water at these low angles. But what we found was that if waves are breaking and there's foam on the water surface, what that foam does is instead of that light sort of bouncing off the water surface like a mirror and off into eternity and we don't get any reflections back, was the foam scatters the light. And so you get this scattered reflection, and so some of it comes back towards the LiDAR scanner. And so we actually get returns off of the water surface with a scanner that should not give us returns off of the water surface at this low angle. So this was really exciting, and I'm going to play that little video one more time. Maybe not.
It's going.
Oh, was it going? There we go. And so you can see we shoot a really narrow profile directed offshore, and we shoot it over and over and over. And what you get are the returns. This is the water surface. You can see a wave incoming towards the beach. This is during a big storm. That's a big wave at the beach, a big bore. It breaks at the shoreline, and then this is the swash running up the beach. And you can see on some of them, they actually comes up and hits the dune. And I think there was one at the start of it where the wave hit the dune and reflected back off and collided with the next incoming wave. So we can get really, really detailed measurements of wave run-up from a remote location during the storm. And run-up has been sort of a traditionally difficult quantity to measure. Folks have done it for a while using the Argus video camera, but you need to be updating your topography to actually make those calculations correct. And so what's great about this is not only are we getting the position of wave run-up on the beach, but we're getting the elevation of wave run-up. And the elevation of wave run-up is what everybody tries to predict, because that's what tells you how far up onto the beach your waves are going to get to, and then therefore what your storm impact is going to be. So we were really excited when this worked. And so what we did was we installed